I'm going to tell you the story of the very first accurate measurement of the circumference of the Earth. It was done by someone who was born over 2,200 years ago, a Greek librarian named Eratosthenes. And you'll see that I've pre-drawn and written this because I didn't want to spend 10 minutes writing his name. But he was a librarian of the Library of Alexandria. He was also just a generally very smart and capable man, as you'll see by his head, which contains lots of ideas inside explaining its shape. And he was not only a mathematician and a geographer, but he was also a poet, ladies, and he was a musical theorist and probably was a very good cook and probably was a great snowboarder, but just could do a lot of things. So it's not a surprise that he was the first person to figure out roughly the size of the Earth. So here's how he did it. He, as I mentioned, he lived in Alexandria. I'm just going to fluff up his beard. But he would travel, and so he was traveling through the town, the city of Syena. And he was walking one day. The date was actually same as today, June 21st, the summer solstice, which is when the sun is highest in the sky. And on that day at noon, he was walking in Syena, and he passed this well. It's a lovely well. It's got water at the bottom. And he noticed that he could see the reflection of the sun at the bottom of the well, and there was no shadow in the well. So what this told Eratosthenes is that the sun's rays are coming straight down at that time and at that place. What he also knew is that on that same date, at the same time, in his city of Alexandria, there was a shadow. So he would be looking at a building. It's an obelisk because, of course, it's an obelisk. And it has a bit of a shadow, which is where the sun's rays don't reach. So that means that the sun's rays are coming from a bit of an angle, out of his nose, I guess. But they're coming from a bit of an angle. And this is huge. This is a huge discovery because it tells him that the Earth isn't flat. The Earth can't be flat because otherwise these angles don't make sense. The only way this makes sense is if this obelisk was actually tilted a little bit due to natural curvature of the Earth. So at that time, obviously a lot of people thought the Earth was flat, and you can't blame them. It's pretty big and it looks flat. But Eratosthenes was able to picture the Earth as a result of this observation, more the shape that we know it to be, round like this. And in order for these shadows to make sense, the tower, the obelisk in Alexandria had to be along the curvature a little bit away from this enormous well, and had to therefore have the sun's rays strike it like this, creating a shadow on the side because it's a little bit tilted in relation. Okay? So how do we go from having all of this information to getting the information we want, which is the size of the circumference of the Earth? Well, it helps a lot that we're working with parallel lines. The sun's rays are parallel. So when you're working with parallel lines like this, and you also have a line that crosses them, and that is the exact angle of the tower, the obelisk in Alexandria, then you know that the two interior angles, here I'll mark them in blue, the two interior angles here, this one and this one, are the same. That's just something that he would know from geometry, that the angle here between the obelisk and the edge of his shadow and the corresponding angle down here would be identical. So what is that angle? He just measured it. That's not super hard to do. He measured it, and it was 1/50th of a circle, about 7.2 degrees. So that means that therefore this is also 1/50th of a circle, which means that 50 of these pizza slices, let's say, fit into the large pizza that is our home, the Earth. I'm not counting, I hope you're not either, but let's say that this is 50, okay? And if there are 50 of these pizza slices and 50 of these tips, then there's also 50 of these crusts here. So if you can figure out what this is, if you can figure out the size, the distance of this, and you multiply it by 50, then you've got the answer here. So how do you measure this? Well, the first thing he did, He runs a library, so this is not a surprise. He did what any of us would do. He just looked it up. But then to confirm that that number was actually accurate, he did what any of us would do. And he got his camel and, okay, there we go. And he walked his camel from one city to another. And he knows roughly how fast his camel walks and how long it took him. So using all that, he was able to confirm that this is about 5,000 stadia. And stadia is the plural for stadion. One stadion is a Greek unit of measurement. It's somewhere between a fifth or a sixth of a kilometer. And the reason that we don't know exactly is that, very unhelpfully, different cities used different sizes of stadia. So we're not positive which one he went by. In fact, he actually wrote a book about this whole thing. It's called something like, "Here's How I Managed to Figure Out the Circumference of the Earth." However, that book was lost or destroyed, and we do not have it, unfortunately, so we don't know. We can guess that it's about a fifth or a sixth of a kilometer, which means that 5,000 stadia times 50, okay, times 50 to get the full thing, is 250,000 stadia, and in kilometers, that's about 45,000 kilometers. So how accurate is that? How good is that answer? Well, with our fancy modern knowledge, we know that the circumference of the Earth is about 40,000 kilometers, which means that he was off by about 5,000 kilometers, which is more than 10%. And that's not terrible. I mean, that's actually pretty good for over 2,000 years ago, but it's also not amazing. I mean, over 10% is quite a bit of margin of error. So what accounts for that discrepancy? Because if you look at his theory, you know, this angle exactly equals this angle. It's not roughly within 10% of this angle. So where's the discrepancy? Well, this distance probably wasn't exactly 5,000 stadia. His camel might have gotten tired or thirsty or grumpy, or he might have measured this angle a little bit off. But also, you know, the Earth is not perfectly round. It has some lumps and bumps. I mean, it's not that young anymore, and it's a little bit oblong. Not quite as oblong as I drew it, but it's a little bit oblong. It's not a perfect sphere. We usually don't say that because it's rude, but now that we know the Earth is a slightly different shape from what he was assuming, which is a perfect circle, and we know a more accurate distance here, more accurate angle, if we use our modern, more accurate assumptions and plug it into his calculations, we actually end up with an answer that's within 0.16% of the actual circumference of the Earth, which completely proves his method and proves his thesis for a guy operating in 240 BC with just a compass and a camel. That's not too shabby.